Hello, everybody. So let's go ahead and get started on a three-part lecture. This lecture and the following two are very connected to each other, and it's actually kind of tough for me to figure out exactly how to break these up. I've done as good of a job as I think I can, but these next three lectures are all very connected to each other. And because they really all have to do with looking at a function and just graphing it. So these three lectures really boil down all to just here's a function, graph it, and make that graph look good. And so just as a little overview of what these three lectures will look like. So today's lecture, you can see it's titled Shapes of Graphs. And so really what we're going to be looking at today are just important characteristics of functions and of graphs, and sort of talking about what those actually mean. And we'll do a little bit of algebra to describe those characteristics. So just as a quick example, we'll get into this later, just talking about where a graph might be increasing or decreasing. That's a characteristic of a graph. And we'll talk a little bit about how to actually figure out where it's increasing and where it's decreasing in this lecture. In the next lecture, we're going to go more in depth into that algebra. So once we actually say, hey, now we know how to find where a function is, for example, increasing or decreasing, we can actually go ahead and find where it is actually increasing and decreasing. So what we're doing there is we're taking that algebra that we've looked at and we're going more in depth to it. And we're actually using that to describe the function itself. And then in that third and last lecture, we'll basically put everything that we've learned together and we'll actually graph these functions and we'll go through how to actually graph those. With that being said, let's go ahead and get started into this. And before we actually get started on any material, I just want to remind us of domain. So domain is something that is very easily forgotten. I myself forget it a lot of the time, but it is critical. It's something that we don't want to forget about. On these functions that we're going to try and graph, we have to care about domain because, for example, if the function doesn't even have, for example, x equals 3 in its domain, if you try to graph it at x equals 3, you're going to get stuck. And so just keep domain in the back of your head as much as you can. Always keep that there in the back of your mind, thinking about it. So let's go ahead and get started. So the first couple characteristics of these of any function of a graph should be fairly simple, or they should be review. So positive and negative for a function. So we'll say a function f of x is positive if it's greater than 0. It's negative if it's less than 0. That should be pretty straightforward right there. So positive, negative, one way to describe a function. Increasing and decreasing is another way to describe a function. And I'll list two ways to show this, or to state this, I should say. One is simple. As x gets larger, so does y. So you could think on a graph, as you move from left to right, your function should go up. So as x gets bigger, so does y. Obviously, you could flip that around. You could say if x gets smaller, y also gets smaller. But this is our better way of looking at it. Decreasing, as x gets larger, y gets smaller. And so that's just a decreasing function right there, kind of just the opposite of increasing. Another way to say this, it looks a little bit more complicated, but it's a little bit more rigorous. And that's to say that if x1 is smaller than x2, so I'm just saying, hey, I've got two x values here, and one of them is bigger than the other. So this bigger one, I'm going to call x2. If that's the case, then the function evaluated at x2 better be bigger than the function evaluated at x1. And so really what we're seeing there, let's just say we have a function x f of x right there. If I've got an x1, let's go ahead and move this down there. If I have an x1 and an x2, then on this function here, you can see that if x1 is greater than x2, or excuse me, I misspoke. If x1 is smaller than x2, which we can see is the case here, then my f of x1 better be smaller than f of x2. And that's definitely the case right there. So that would be an example of an increasing function. And in this case, it would really, we could only be sure of ourselves that it's increasing between x1 and x2. And even then, you might even have some issue like this, where it increases and it decreases. It goes up and it goes down. So you do want to be careful there. I won't get into much of that sort of trickery yet. But yeah, just be careful there on increasing. Decreasing would just be the opposite. If x1 is smaller than x2, then f of x1 would be bigger than x2. And so just the opposite there. But increasing, decreasing should be fairly straightforward, fairly review there. Let me make a note here that this is increasing for this picture that I have drawn. Graphically, we're probably more used to seeing this here. I'll go ahead and mark in the blue where this function is increasing. And I'll go ahead and mark in orange where it's decreasing. And so you can see right here where I'm currently drawing the blue, that's just saying as my x gets larger, as I move from left to right for my x, my y is increasing. It's going up. It's also getting larger. So on these blue sections, we're seeing exactly that. We're seeing the y values get larger as I move from left to right. And on the orange, we're just our y values are getting smaller as our x values move from left to right, as our x values get bigger. So increasing, decreasing right there, basically just, hey, as you read from left to right, is the function going up or is it going down? And that's increasing and decreasing. So there we go. I've even labeled here. You could do this same exact work. Let me just copy that all down. In these blue regions, I'm increasing, and in the orange regions, I am decreasing. And so what I'm noting here are these points A, B, C, and D, because that's actually where that's sort of the switch points where the function is switching from increasing to decreasing. But there's something else that I notice about A, B, C, and D, and it's actually a very key aspect of derivatives. And it's that A, B, C, and D all have f of, let's say, smiley face, just for calling it A, B, C, or D, f of A, f of B, f of C, f of D. And if I take a derivative of that, I get 0. Basically, this is just my complicated way of saying, hey, the slope is 0 at A, B, C, and D. And so that right there is actually, that's sort of an indicator. That's something that we can see on this graph of like, hey, this is an important point. A, B, C, and D, each of those coordinate points are important because the derivative is equal to 0 there. And what we're noticing here is that at each of those points, the graph switches from increasing to decreasing. And so I'm seeing this connection between my derivative being 0 and the function switching from increasing to decreasing or from decreasing to increasing. And here's even more so what I notice here. If we try and draw some tangent lines, if I look, and I'm going to go ahead and get rid of the blue and the orange here, we can remember that where this is increasing and decreasing. So I'm increasing, let's say in between B and C, I am definitely increasing there. My function is going up. And so if I draw a tangent line here, let's say I pick a point and I draw a tangent line. That tangent line has a positive slope. And so that means that the derivative is going to be greater than 0. And then very similarly, in this region here in between A and B, I'm decreasing. So my tangent line has a negative slope. That's saying that my derivative is negative. And so what we're seeing here is that when a function is increasing, let's go ahead and write this down. When a function is increasing, the derivative is greater than 0. And then when my function is decreasing, I have exactly the opposite. My derivative is in fact less than 0. It's going to be negative. And so that's a great indicator right there where we can see, hey, if I want to know whether my function is increasing or decreasing, if I'm maybe confused by just looking at it on the graph, or maybe I don't even have a graph, I can just calculate the derivative. And if my derivative is positive, my function is increasing there. If my derivative is negative, my function is decreasing there. And so everything I've just said right there, I can just summarize. This is basically exactly what I just said. If f prime of x is greater than 0, if it's positive, then f, the original function, is increasing. If f prime is negative, then f is decreasing. The original function is decreasing. So just a recap of what we've talked about so far, we've seen positive and negative being a good indicator, a good descriptor of functions and graphs. We're also seeing increasing and decreasing, which is a little bit more profound of a description. It helps us a bit more than just positive negative does. Both important, but increasing and decreasing are definitely sort of more key because they involve derivatives here, and just reminding ourselves that in those regions where the derivative, where the tangent line has a slope that is positive, that's increasing, and then vice versa with decreasing. So let's go ahead and look at an example here. So we're going to look at the function 5 times 2x plus 3 all raised to the 4th. And I want to find out where that function is increasing or decreasing. And so we're going to actually have to take a derivative here. And let's go ahead and do that. So if we take a derivative, we can just use the product rule, or excuse me, the power rule, with a very simple application of the chain rule as well. So f prime of x, I have my 5, that stays out there because it's just a constant. I drop the 4 down. I subtract 1 from my power, and then I have to multiply by the chain rule term, which is the derivative of 2x plus 3. And so we have 20 times 2x plus 3 to the 3rd multiplied by 2. So I have 40 times 2x plus 3 cubed. And so when I'm looking at this, I'm asking the question, hey, find where this is increasing or decreasing. And we've said that when f prime of x is positive, that means that the function is going to be increasing. And then when f prime of x is negative, the function will be decreasing. So this is actually just a straightforward algebra question at this point. When f prime of x, given by this, is greater than 0, that's when my function is increasing. And we've dealt with inequalities before, so let's just deal with them one more time. Let's go ahead and add a new slide here. So we've got f prime, and I'll go ahead and write this up on the top. F prime of x equals 40 times 2x plus 3 cubed. Got that right there. And now basically just to find increasing and decreasing, we're just going to set up two inequalities. I'll write this out fully. F prime of x greater than 0, f prime of x less than 0. F prime of x, I have a formula for it. We just found it. 40 times 2x plus 3 cubed greater than 0. Let's give myself a little bit more space here. And then very similarly, less than 0 right there. And so we'll just simplify this down. Divide both sides by 40, nothing changes there. And then here, I can take the cube root of both sides, and nothing changes again. I just have my 2x plus 3 on each side. And we're just simplifying down this very simple inequality here. Again, give myself some more space here. So we're going to end up with x greater than -3/2. And then over here, we're going to end up with x less than -3/2. And so right there, that's just our answers. That exactly tells us here. Let's go ahead and label it nice and interestingly. X increasing, x decreasing. We'd probably use interval notation here, and I'll do that in a second. But basically, we found our answer here. We've said, hey, here's my derivative in the blue, in the turquoise blue up at the top, and I want to know where my original function was increasing or decreasing. So I just set that derivative to be greater than 0 or less than 0, and that's just an inequality problem that we should be comfortable solving. And we end up with, hey, it's increasing when x is bigger than -3/2, and it's decreasing when x is less than -3/2. We'll get into this more a bit later, but you should be able to tell here that when x is equal to -3/2, you're going to have a slope of 0. And that's going to indicate likely that we have a maximum or a minimum. And we'll get into all that a little bit later. But that's something that you might be able to tell now. So we've got these regions here. What I could add in, and I'll kind of just squeeze this in here, is that we could say interval notation, -3/2 to infinity, and then here we could say -∞ to -3/2. I recommend being comfortable with interval notation. If you're not, I recommend reviewing it. It's definitely not necessary, but it's really, really helpful. It's just a great way to write intervals out, especially when they get complicated, and with unions and things like that. So I recommend learning interval notation or reminding yourself of that. So just kind of stepping back here, I want to go back to this original graph that I had, and I'm gonna copy this over. So we're looking at this function, and we're thinking about how can I describe this, and we can say positive or negative. Very clearly, the function is positive on this highlighted portion, and it's negative on this different highlighted portion here. And then where it's increasing and decreasing, that has to do with what the slope is. And so on all three of these highlighted sections, my slope is positive. My tangent line has a positive slope. My derivative is positive. And so that's going to be increasing right there. And then on these regions, A to B and C to D, I'm going to have a negative derivative, a negative slope of my tangent line, which means that I'm going to have a decreasing function. And we're seeing these points A, B, C, and D as being these sort of switch points. And when that happens, when my function switches from increasing to decreasing, we typically have a slope equal to 0, as is indicated by just these tangent lines that I could draw right there. And you can probably also tell that A and C are what we'd call local maximums. Again, just to be a little bit simpler with that, we could just say they're a maximum. And B and D are going to be minimums, right? They are the B and D are the smallest points within a nearby area. They're sort of, if you look locally, if you were to zoom in, we could actually do it. If you zoom in really closely and you just look right around here, B is the smallest point. A is the largest point. We might call that a maximum. And then same thing with C and D. C is the largest point in just this little area. D is the smallest point in that little area. So again, maximum for C and minimum for D. We'll get into a lot more of that later, but we're seeing now that we can very easily do this algebra technique. We can take a derivative, we can set that derivative greater than or less than 0 and solve a simple inequality problem to answer whether it's increasing or decreasing. Great. So now that we've gone through all of that, we're going to talk about this idea of concavity. And this, and we should be able to go through this a little bit quicker because it's basically the same concept. Or excuse me, it's basically the same steps as increasing and decreasing. The concept is just a little bit different. So let's go ahead. I'll skip past all this work here. We just did all that. So let's look at concavity. So this idea of concavity, we can describe it as being concave up or concave down. You could say the concavity is up or down. And a very sort of intuitive way, a very colloquial way of thinking about this is just saying, hey, is my function smiling or is it frowning? And so exactly what I mean by that, let's take a look at a graph right here. And I'm gonna focus in on just a certain part here. I'm gonna focus in just on this blue right there. I'm gonna be very careful about that little point right there that I cut it off at. But on this blue part, if you were to ask yourself, hey, is this smiling or frowning? Well, maybe I put some eyes up here and that looks like it's frowning to me right there. And so because it's frowning in that blue, I'm gonna say that it's concave down. All right. And then very similarly, you can see here, it also looks like it's frowning. Concave down again. Let's go ahead and label that. Concave down in blue, and then in orange, I'll do concave up. And so concave up, you can see right here, if I put some eyes right there, that looks like it's smiling. And then same thing here on this outer edge right there. Maybe that looks like a big smile there, but it looks more like it's smiling rather than it's frowning. And so we would say that those are concave up in those orange sections, and the blue would be concave down. And that's a very intuitive way of thinking about this idea of concavity. Basically, why we care about concavity is there are certain properties of functions that determine whether it's doing this frowning or smiling sort of motion there. It actually has to do with the second derivative, and we'll get to that in a little bit. But basically, this idea of concavity is important just for that reason. We care about when functions sort of have these different types of curvatures, this curvature that mimics a smile versus the curvature that mimics a frown. Yet again, you can see A, B, and C. I've got those points labeled. I can redraw my regions here like we had it. Right there. And actually taking those away, you can look and see at A, B, and C. If you look at all of those, maybe focus on A for now. That switch point, that point A, it kind of happens right in between this maximum and this minimum, that high value and that low value. That's not always the case, but here I've made this graph be fairly symmetrical. So you're seeing again that this B point is kind of halfway in between these, and in between these maximums and minimums. That doesn't always happen, but what we're seeing here is that as I go from this increasing to decreasing and I keep decreasing, it does kind of hit this point right here where that concavity does change. And we'll get into what that means more later, but just sort of a look ahead. So concavity, we've seen smiling and frowning. That means concave up and concave down. Here's a more mathematical way of describing concavity. We'll say a function is concave up when the function is above its own tangent line. So what that means is that if I were to draw a tangent line on the function, if the function is above it, then that means it's concave up. And let's actually look at an example of that. So here's a great example here where I've got my point there in orange and I've got a tangent line in blue and the function in red. And in this case, that red function is above, it's higher than, it has greater y values than that blue tangent line. It's above that blue tangent line, so that means concave up. And I'm going to keep that red function the exact same, and I'm just going to change the tangent line to just looking at a different point here, maybe off more on its side. Here, that red function is still it's still above. It's still larger than that blue tangent line, in which case we would again say concave up. So going back here now to concave down, it's just the opposite. A function is concave down when the function is below its own tangent line. So looking at some of these examples here, I've got that red function here, and I draw a tangent line at this particular orange point, and that blue tangent line is actually above the red. You could say the red is below the blue tangent line. The red function is below the blue tangent line. So that's going to be concave down. Again, sort of changing that point, that orange point, to just something different, just as another example. We've got our tangent line in blue, the function in red. The function in red is below the tangent line in blue, concave down. A little bit more rigorous of a definition than saying smiling or frowning. Maybe a little harder to think about, but good to see there. So this next definition, I'm going to show one more definition of concavity. This is probably the most important definition. This is the definition that you're going to use the most. And it has to do with the second derivative here. So a function is concave up when the function has a second derivative that is positive. And then it's concave down when the second derivative is negative. So you can see why I spent so much time talking about increasing and decreasing and how to find that regions, solving those inequalities. It's because those inequalities are going to pop up yet again. When we want to find the concavity of a function, we just have to take two derivatives, then we have our second derivative, and then once we have that, we can then just set up an inequality. And then once we set up that inequality, that's going to give us our regions that we care about. And so let's go ahead and do that, and we should be able to do this a little bit more quickly than we did last time with the increasing decreasing. So let's go ahead and look at this function 3 multiplied by 2x plus 5 to the third, and we're going to take two derivatives here. And I'm going to take these a little bit more quickly than before, just because we've seen the power rule, we've seen the chain rule. We know how to do these. So 9, because I'm dropping that 3 down. So I'm taking this 3 and I'm dropping it down. And 3 times 3 is 9. Times 2x plus 5, and I just take 1 off of that power, and I multiply that by 2. That's my chain rule term right there. So I have 18 multiplied by 2x plus 5 to the second. F double prime. We're going to drop that 2 down. It's going to multiply on that 18. I'm going to subtract 1 off of the power. So I just have 2x plus 5 to the 1. And I'm going to multiply that again by a chain rule 2. That's the derivative of the inner function, the 2x plus 5. I get 72 times 2x plus 5. And that's my second derivative. And at this point, it's basically the same thing that we did before. We saw, so we had all of that work. Let's go ahead and outline it in the same way. Here it's the second derivative is 72 times 2x plus 5. And so if we want to find where it's concave up and concave down, sometimes you'll see people just write CU and CD, but that's totally fine. I'll know what you mean. So concave up, we're just going to set that second derivative greater than 0. For concave down, we set that second derivative less than 0. Now it's just plugging and chugging. We got 72 times 2x plus 5 greater than 0. 2x plus 5 greater than 0. 2x greater than 5. Excuse me, negative 5. Subtracting 5 from both sides. X is greater than negative 5 halves. And then the work over here is basically the same thing, just a slightly different inequality sign. X less than negative 5 halves. And so if we want to, we could do interval notation. We could say negative 5 halves up to infinity. And here we could say negative infinity up to -5/2. Open brackets on all of those. And so that's exactly it. That's my concave up and my concave down. And it's just setting that second derivative either greater than or less than 0, depending on which one you're talking about right there. And so while we're there, I want to stop for a second and do just a little bit of recap on what we've talked about so far. So we've talked about three characteristics. And these three characteristics are going to be, first, positive, negative, found by just looking at f of x greater than 0, f of x less than 0. Second is increasing, decreasing. And that's found by setting f prime of x greater than 0 or f prime of x less than 0. And lastly, we've talked about concave up. We'll say concave up or concave down. And that's when f double prime of x is greater than 0 and f double prime of x is less than 0. So you should see a pattern here. You should be able to tell that the function, the derivative, and the second derivative all being greater than or less than 0 those are important things. That's really what we care about for a function. And so looking way ahead into future lectures, when I actually give you a function f of x and I say, hey, graph it, basically what it's going to boil down to is you finding out, hey, where is it positive and negative? Where is it increasing and decreasing? And where is it concave up and concave down? And that's actually all the information that you really need to graph it. And we've seen how to do this with the algebra today that we've been dealing with. That's going to be just setting up these inequality equations like we did here. Like we did in this work. We did this here for concavity. We did it before with the increasing, decreasing. So far, we're just looking at how to do this algebraically with the inequality algebra. We'll look at more ways on how to do that in future lectures. But for now, we've basically got it. We can just take the function, the derivative, and the second derivative, and just find what regions they're positive or negative. And that's going to give us a lot of information there. Great. As I've alluded to, the actual part here, the actual points where the function is equal to 0, or the derivative is equal to 0, or the concavity, or excuse me, the second derivative is equal to 0, sort of those switch points, like we said, those are important as well, and those actually help us. So like before, we had that here, A, B, C, and D. Those were points where the first derivative was in the process of switching from one sign to the other, so from positive to negative or negative to positive. And what we noticed there was when that happened, we had f prime of x equal to 0, right? And then very similarly to what I just showed there, we would also have that on concavity. At these points A, B, and C, as we said, the concavity is switching from negative to positive. And so this right here at that point A, as well as B and C, that is a point where f double prime of x is equal to 0 right there. And so obviously, like we care, just like we care about the function, the derivative, and the second derivative being positive or negative, we also care about where each of those are equal to 0. And right now, we should be familiar with a name of at least one of these. This is a root or a 0 or an x-intercept. Squeeze that in there. X-int. As we saw before, we can surmise that this is going to be a max or a min. I'll make a note here. I'll put a little asterisk. It doesn't have to be a max or a min, but for now, let's just think of it that way. And then for this second derivative, well, we haven't come up with a name yet, and I'll get to that in a little bit. So as I just said, skip past this work, we did that already. We have names of these points when we have each of these function, derivative, and second derivative being 0. And so when the function is equal to 0, then at that point, we call that a 0 or a root, or you can call it an x-intercept. 0 is probably the most common naming that we give it. And then when f prime is equal to 0, when the derivative is equal to 0 at a particular point, that point, like I said before, I said it's a max or a min, and I put a little asterisk there. Instead of saying a max or a min, we'll likely say it's a critical point. And so ingrain that in your head. If the derivative is equal to 0, that point is a critical point. So going back to that lovely graph that we've been looking at before. Oh, let's go ahead and leave that. So at A, B, C, and D, we have a derivative that is equal to 0. That means that A, B, C, and D are all critical points. And then as well as the derivative being 0, giving us a critical point, if the derivative is actually undefined, that also gives us a critical point. And so a great example of this, let's go ahead and sketch this. Sketch a function here real quick. Just like that. So if that's my function, x, f of x, then right here, my tangent line, I'll draw it dashed. So that's not an asymptote. Let me be clear. I'm just drawing it dashed because I want to make it look nice. But that tangent, that dashed tangent line in the blue there, that is vertical. That means that my slope is undefined. It's infinity. It's undefined, either way you want to say it. And in that case, this point right here, A, that would be a critical point as well. So a critical point is where my function has a derivative which is either 0 or undefined. That's a critical point. And then I cannot ingrain this enough. I put before, I said, hey, when the second derivative is 0, oh, we don't have a name for that. I'm going to hold off and I'll get back to it. Well, I'm back to it now, and I want to just state this definition very blatantly, very clearly. An inflection point, so that's the name, inflection point, that's what I'm calling that point, is where a graph changes concavity. Now, let me be very clear. A lot of the time, most of the time, that's when f double prime, when the second derivative is equal to 0 or undefined. But it does not have to be, all right? An inflection point does not have to occur when the second derivative is equal to 0 or undefined. It generally does, but it does not have to. The exact definition of an inflection point is where the graph changes concavity. And so again, going back here, we've seen this before. At A, B, and C, we saw that in those regions, the graph changed from being frowning in the blue to smiling in the orange. So that A, B, and C, those are each going to be inflection points because the graph changes concavity. It is quite possible to have a function where the second derivative is 0 at that point, but the function does not change concavity. Let me draw a great example of this for you. So what I'm going to draw here is x to the fourth, and I'm just going to sketch it. Ooh, not a very good sketch. So this is a rough sketch of x to the fourth here. And it turns out that at that point, right there at the origin, f double prime, I'll note f double prime of 0, it equals 0. And so the second derivative is equal to 0. So a lot of people say, oh, great, inflection point, inflection point, inflection point. But this is not an inflection point, because as you can very clearly see, this graph in the red, it's always smiling, right? Put my eyes right there. That's a big old smiley face right there. And so at this point here, the graph does not change concavity, even though if you actually evaluate it, the second derivative is in fact equal to 0. You can do that. You could take two derivatives of x to the fourth, plug in 0, you're going to get 0. I can just do that really quick right off on the side. X to the fourth, 4x cubed is my first derivative. My second derivative is going to be 12x squared. If I evaluate that at 0, that's going to give me 12 times 0 squared, which is just equal to 0. So you can see the second derivative is in fact 0 at that point, but the graph does not change concavity. So I can't emphasize that enough. An inflection point is where the graph changes concavity. It is not necessarily where the function has a second derivative equal to 0 or undefined. A lot of the time that happens, but not all the time, as in this case right here. So there we go. That's the sort of let's pop back over here. Everything we just talked about there is this portion of this sort of recap slide, and then we've seen before this portion here. Let's do an example for this portion. So I'm going to give us a function. I'm going to say, hey, tell me where all the zeros are. Tell me where all the critical points are, which, remember, like we said, a lot of times they're max and mins, but they're not always. And then here we call that maybe an inflection point, but we weren't sure, right? It depends on if the concavity changes. Let's look at an example where we actually go ahead and find the those 3 points. So I've got x squared times x minus 2. And so I want to find zeros, critical points, and where f double prime of x equals 0. Let me be very clear here. You'll see this a lot. You'll see this verbiage or this jargon used a lot. Where f double prime of x equals 0, a lot of times you'll see this written as possible inflection point. I'm gonna give myself some more space there. Sometimes called a pip, or even just writing possible IP. And so if I give you a question, if you ever see a question, an example that says, hey, find the zeros, find the critical points, and find the pips, find the possible inflection points. That's just saying, hey, find where f double prime of x equals 0. And we call it a possible inflection point. We call it a pip because we don't know if it's an inflection point. The second derivative being 0 does not guarantee that it is an inflection point. But it's a good sort of check for, hey, if the second derivative is 0, it might change concavity. So let's go ahead and just find all these points where f double prime is equal to 0, label them pips, and then we'll check and see if the concavity actually changes. And we'll do more of that in future lectures, but I'm just kind of alluding to that now. Great. So let's go ahead and start right off here. So I'll go ahead and give us a new slide. Nice clean slate to work with. So if I want to find zeros, I'm going to set f of x equal to 0. Well, my function is x squared times x minus 2. equals 0. So I split this up into x squared equals 0 and x minus 2 equals 0. I get x equals 0, and I get x equals 2. This is a notation that I use a lot. It's not as common in other mathematicians. X sub z, I label it z for 0. Sometimes you might even see me say xz1 and xz2 just to indicate, hey, there's multiple of them. That's a notation that I like to use. You do not have to use it, but you're welcome to if it makes sense to you. Just really being clear here, my zeros are at x equals 0 and x equals 2. I can't emphasize enough just while we're here. This is a general mathematical sort of thing. Writing your answers out in like a sentence format like that, saying, hey, the zeros are at x equals 0 and x equals 2. That's perfectly acceptable. And it really gets the point across very clearly using some English, using some words there. So yeah, there we go. X equals 0 and x equals 2. That's going to be the portions of our graph where we have an x-intercept. Now, what you could do here, we're not asked to do it in this example, but what you will eventually do is you'll recognize that this 0 and 2, those x-intercepts, that's going to give us regions that will help us determine where the function is positive or negative. We'll get into that more later, but here we've got our zeros, and that's great. Let's go ahead and find the critical points. Go ahead and highlight that. So we're going to find critical points here, and that's where f prime of x is equal to 0, and f prime of x. So we're actually going to have to take a derivative here, and you could use the product rule. You'll notice that I've got an x squared and I've got an x minus 2. Those are two portions that are multiplied by each other, and they're independent. But I don't want to use the product rule. The product rule is annoying. Maybe I forget the product rule. Maybe I'm bad at the product rule. Whatever your reason is, my reason is just I don't want to do it. I don't like doing it, and we don't have to. So I'm actually just going to distribute this out, and now I can take a derivative, and it actually is just a lot easier. I just use the power rule very simply, and then here I could actually factor. And that's a lot faster, I think. I think it's a lot easier too, just to rewrite that function, then take a derivative, then factor it. And so what we're doing here, we're gonna set f prime of x equal to 0, and we're also going to set f prime of x equal to undefined. Do not forget that undefined. A critical point is where the derivative is equal to 0 or undefined. In this case here, this never happens right here. We never have the derivative being undefined. There's no way for this x times 3x minus 4. There's no way for this to be infinity, unless x were infinity, but that's not really a point that we care about. We want to see, hey, is there a very specific point where x is equal to, or is there a specific x where the derivative is equal to infinity? And that can't happen right there. So we don't have to worry about that. That's okay. F prime of x equals to 0. I have x times 3x minus 4 equals 0. And so we have x sub c. I call it c for critical points. And I won't bother showing that work explicitly right there, but we've got our two answers right there. That should be fairly straightforward to solve 3x minus 4 equals 0. And so we have x sub c. Again, you could label them x sub c1, x sub c2 if you felt like it. I won't bother here. Just x sub c. Hey, there's our critical points. That's great. All right. Last, but certainly not least, let's find where f double prime of x is equal to 0. And so we actually had the derivative here. Looking back at this step of the derivative, you're welcome to use this step, but again, I don't want to use the product rule. Let's just use this step. This is the derivative. It's maybe not simplified and factored how we want it, But it is the derivative. So let's just copy that over. So 3x squared minus 4x. 3x squared minus 4x. And I'm going to take a derivative of that to get my second derivative. 6x minus 4. And then I set f double prime of x equal to 0. And that's, let's just go ahead right there. 6x minus 4 equals 0. We're going to get x is equal to 2/3 right there. And so yet again, so I've been using x sub z for my zeros, x sub c for my critical points. Here, I'm going to actually say x pip, possible inflection point, 2/3 right there. I will mention too, I haven't asked us to do this in this problem to find where f double prime of x is equal to undefined, but I very well could. I don't here because there's no way for it to be undefined. 6x minus 4 is just a line. That's always defined. That has a domain of everything. That's totally fine. And so we never have undefined there. But yeah, so here we just got our x pip, our possible inflection point. That's where f double prime of x is equal to 0. We've got that at 2/3 right there. So again, just a big recap here of everything that we've seen. So we've said, hey, there's 3 primary ways that we're going to describe a function: positive and negative, increasing and decreasing, concave up and concave down. And we can talk about those intervals, the regions that each of those descriptors occur in, by looking at where the function, the first derivative, and the second derivative are each greater than 0 or less than 0. And then obviously that leads us to also wondering, hey, well, what about when each of those are equal to 0? Well, when the function is just equal to 0, we have a root or a 0 or an x-intercept. And then here, I'll go ahead and erase that max min. Let's just write critical point. Critical point. And heck, let's actually, let's not leave this off here. We definitely care about f prime of x being undefined. That's also a critical point. And then likewise right here, f double prime of x is equal to 0. We also do care about f double prime of x being undefined. And we'll go ahead and call these pips, possible inflection points. And so we definitely care about where those are all equal to 0, where the function is, where the derivative is, and where the second derivative is. I will mention one other thing as well. Here, so for both of these bottom guys, for the first and second derivatives, I've listed, hey, 0 and undefined, 0 and undefined. But up here, I just listed 0. Well, if the function is undefined, that's just a domain. That's just a domain issue. So again, like I mentioned in the very beginning, always keep domain in the back of your head. We care about domain. But here, positive, negative, increasing, decreasing, concave up, concave down. We care about our derivatives and where they're positive, negative, or 0. And that's going to give us a whole lot of information for how to actually graph these functions. So that'll be it for the lecture. We'll go ahead and get into much more detail and depth of how to find these without really doing a whole lot of that inequality algebra, and even how to just kind of find these maybe even a little quicker as well. And then we'll get into some actual graphing after that. So we'll go ahead and call that for the lecture today, and that'll be it.